So great. Thanks a lot, Arya, Oliver, and the organizing team. My name is Santosh Gurunath. I'll be talking a little bit about electrolyzers, primarily looking at it from an industrial commercial standpoint, right, rather than an academic standpoint or research standpoint, which has been in the scope of discussion so far. So covering what are the types of electrolyzers which are already commercial to a certain extent. Focus quite a bit of my time on some of the innovations or some of the commercial kind of operations of electrolyzer companies who are taking a very different approach rather than the conventional alkaline or PEM. And then also spend a little bit of time on the, let's say, impact of some of these innovations on the levelized cost of hydrogen, right? And looking at what actually moves the needle as such. Right? So very quick introduction. So I'm been running my company, Umagine, for the past 6 years now. Originally started in the Netherlands, not too far away from Denmark. We were focusing at that point on solar, started some hydrogen work as well. Currently, we do two main things. We do policy work, start consulting work on hydrogen, which could be anything from policies to strategy to engineering across the value chain. And then second, we have our own technology on PEM fuel cells, which we do primarily for stationary fuel cell, stationary applications, stationary power applications, not for mobility. That's a very quick background. Some of the clients which we work with on a regular basis. Um, so, um, so basically, the four main electrolyzer classes, which has been pretty actively kind of talked about or commercialized as alkaline PEM, SOEC, and ion exchange, with alkaline and PEM getting the most, let's say, focus from a large scale commercialization perspective. And there are some of these parameters which kind of differentiate them on temperatures, pressure. So a lot which most of the audience would be aware of, but where I would like to focus a little bit of my time and attention is that with let's say there are definitely certain advantages of let's say alkaline or the over PEM or SOEC, but what we are seeing is let's say even a move towards hybrid utilization of electrolyzers, right? Where there are projects where potentially at in the same project you'll have PEM electrolyzers for your fast moving operations, and then alkaline electrolyzers more for the base load or once things get steady, right? So and then in certain exchanges combining SOEC with alkaline as well, part of that SOEC for your heat integration purposes because it's kind of operational at high temperatures, the steam electrolysis process. So it's in that sense a very interesting kind of point to understand how all these electrolyzers work and potentially kind of combination or hybrid electrolyzer application depending upon the use case might be let's say a way to go rather than a single stop kind of an approach. So spending a little bit more time on each of those alkaline electrolyzers, of course, let's say one of the major challenges is your turn down. I mean, typically at a system level, it does not you cannot get below 30%. Efficiency is more or less average about say 60 to 75%. All of these cost numbers are slightly kind of in comparison with what I think the speaker from Sheestal had mentioned around €1,000 per kilowatt, but we are also already seeing Chinese electrolyzers less than $200 to $50 per kilowatt, and in India of close to about $400 to $500 per kilowatt. So definitely, alkaline electrolyzers have picked up quite a bit of pace with respect to cost reduction and let's say installations as well to a certain extent. Some of the commercial projects, I mean, there are a few projects where let's say 10, 20 megawatt 30 megawatt kind of applications or projects have been deployed. So there is, over the last few years, at least, experience has been gained as such. So coming to PEM, the major advantage of PEM, and that's one of the reasons why a lot of European-based manufacturers look at PEM seriously is very low turndown, right, and also very fast dynamics. Specifically looking at kind of response times of a few seconds compared to alkaline, let's say, which takes several minutes and up to half an hour for ramp up and ramp down because of let's say, the liquid KOH loop as such. But in this case, you can, as it's a solid electrolyte, you can switch very quickly. The efficiency is kind of similar, slightly. You might have certain benefits, about 5 odd percentage on it. Capex is definitely more expensive. You're not seeing a lot of Chinese large scale PEM electrolyzers yet. So the cost is more or less defined still by your, let's say, European players. And then there have been, specifically in Europe, as I said, in Germany, in the Netherlands, a few 10, 20 megawatt kind of units already deployed and operational for the last couple of years. And so So from an RFNBO perspective, early matching perspective, and load following from renewable energy following electrolyzers, where let's say energy storage is not an option or energy storage is kind of very difficult. This is a very interesting kind of technology to apply. Mm, AEM electrolyzers has been kind of touted as, to a certain extent, the next big thing. I mean, has advantages of both alkaline as well as PEM electrolyzers. And there have been certain large scale stack designs which have been kind of which have started testing, although still not as prevalent as alkaline and PEM. But overall, the lower KOH concentration and let's say definitely helps uh, at the same time has the advantages with respect to the ramp ups and the ramp downs compared to that of alkaline, similar to that of PEM electrolyzers. One of the major challenges which I've seen so far with AEM electrolyzers is the lifetime. I mean, we have not come across a lot where we're looking at 80,000 or 100,000 hours of stack lifetime with respect to AEM. So that's an area of kind of improvement in process still under. Uh, SOECs, I'll talk more about it as well, but SOECs is definitely something which I think a couple of Danish companies are also looking at. And let's say in the US, there have been certain factories which have been starting to build on SOECs. And specific, the biggest advantage is your higher efficiency when it comes to, let's say, utilizing the heat from the high grade heat, which is available in an SOEC kind of an operation, and integrating that with a refinery or a fertilizer company, fertilizer plant, as long as there is a need for that, right? So, and there have been certain companies specifically looking at SOECs. Again, the lifetime is yet to be sorted. The cost is still far away from what we can accept from an economical standpoint, but definitely one of the major contenders. So a lot of these vendors have come, of course, much more heavily on the alkaline and PEM side right now. You see Sunfires and the ThyssenKrupps and the Nels, and then in PEM, your Plugs and Siemens, Cummins, and some of the project installations which have happened over the last few years. This might be a little bit outdated, but these are really projects which have been installed and operational at least for a couple of years comparatively. So from an industry standpoint, when we kind of build these projects, we look at a number of different things, right, to make a choice, right? I mean, so this is like a very simplistic comparison, which has been shown here, where we look at the capex, of course, efficiency, the stack lifetimes, availability of technology, the turn down ratios, amongst other parameters, right? I mean, these are some of the basic parameters which we look at, and some of the kind of, from a suitability standpoint, for this was for one of the projects which we were kind of advising in for a large, let's say, 500 megawatt, 600 megawatt electrolyzer, where alkaline and PEM kind of came up on the top from looking at all these factors. And of course, I mean, this is a study which we did a year and a half back. If we do the same study again now, things might change, right? Looking at some of the advancements. Moving into the innovations and electrolyzer technology, so there is high SATA, right, where which there's a lot of money has been pumped into this company, and then there's a lot of talk on, right? So they do where, let's say, they have a kind of a bubble-free electrolyzer, which through which they offer like very high efficiencies, right? So basically, it is basically about similar efficiencies as an SOEC, right? But then operating at kind of alkaline electrolyzer kind of setup, right? So they have a capillary based setup. So some of the details on the electric catalyst side and the mechanisms mentioned over here. So it's something which has a lot of potential with respect to kind of disrupting some of the existing conventional technologies. Sunfire SOEC is something which has been was covered earlier. So again, they've been moving pretty fast from a commercialization standpoint, and you see some of these larger scale SOEC deployments kind of coming up in addition from them. Ceres has been also very active, UK based company, also in the SOEC space. They primarily do more technology licensing, and they have been kind of working together with some Chinese companies, Bosch, also some Indian companies such as Thermax, also kind of demonstrating very, very high efficiency, close to 90-95% of HHV on their electrolyzers, and some of them have been deployed also in India actually for one of the pilot projects for Shell. But there is quite a bit of, let's say, interest in their technology. Enapter is a, I'd say, a fairly well-known name for anyone who is looking at setting up small scale electrolyzers. They have these smaller modules of, let's say, 2.5 kilowatt, zero point 0.5 nm cube, right? I mean, all these smaller boxes what you see on the right hand side. I mean, traditionally AEM electrolyzers, very fast, or let's say turn down, ramp ups, etc. And they have grown a lot over the last few years, and we are seeing some of their larger systems as well. Let's say where they use a lot of these 2.4 kilowatt modules. So interesting approach, specifically now wherever distributed hydrogen production is being talked about, not the very large scale at least, where such AEM electrolyzers have been applied. Um, Cavendish, I mean, another company which, let's say, I've done a lot of innovations on the membrane side, was bought out by Reliance, if I remember correctly. Uh, and let's say, uh, the efficiencies again which they achieved due to the innovations on the membrane side is commendable, and they are moving towards commercialization from what we understand. So another AEM electrolysis, but then slightly different approach, right? I mean, this is a basically carbonate electrolysis, right? Very different kind of stack design, which has been kind of made from more or less regularly available material. They're targeting like $30 per kilowatt on the stack level, and a lot of let's say push towards kind of commercialization happening in this space as well. So again, let's say focus on the AEM side. Finally, coming to Plug Power. Plug Power is of course a well-known name, but over time they have also kind of have been focused on reducing the stack cost, right, as much as possible. I mean, in fact, like over there from the generation one design to the latest design, they have at least achieved 70 to 80% reduction with respect to the stack cost. So there's a lot of focus from their side on the stack itself, not so much on the system side, of course, I mean, where they use existing kind of integration opportunities. Finally, electric hydrogen, again, let's say, in a different approach, but they have scaled up quite fast, looking at very large scale kind of projects, very large scale deployments. I mean, at least looking at 100 megawatt and above. So another company which is kind of looking at it from, I mean, it's a similar approach to an alkaline electrolyzer, but then setting up very large scale projects. Finally, coming to the cost side, so this is again, I mean, an analysis which we did a while back for an alkaline electrolyzer specifically. Let's say taking a 1 megawatt electrolyzer, where you see that let's say the stack contributes to about 35% of the cost. The power electronics and the let's say the gas purification and the balance of systems another 30%, and the other rest on piping, instrumentation, balance of plants, and EPC adding up to, let's say, close to $850 in this case from a cost perspective, right? So if you're looking at it from an OPEX perspective for a similar electrolyzer, of course, you add up all the elements on the electricity side, utilities with respect to KOH, stack replacement, the purification segments, etc. And there's certain. So what we did is we kind of did a comparative on, let's say, very basic for illustration purposes. Let's say base case having a $5 per kg kind of an LCOH. The moment when you decrease that from 50 to 30, you almost have a $1.2 per kg kind of a difference, right? So almost 25% decrease directly on the electricity price. The capex reduction has marginal impact, right? I mean, a reduction of capex of about 20% of the electrolyzer side results in an LCOH impact of less than 5%. So that is something which it does have an impact, but again, I mean, showing that electricity has a much bigger contribution. Load factor impact is something which is really, I mean, having a very big impact, of course, because you kind of oversize your electrolyzer accordingly, or you need energy storage in that sense. So kind of moving from a hybrid model to a solar model, you see some of the differences. So finally, coming to, I think this is my last slide. If you look at LCOH, and we looked at some point of time, what are the innovations you would need to kind of get down to your $1 per kg considering we're at about $5 right now. And I mean, there's going to be a ton load of things which you need to do, right? I mean, of course, on the electrolyzer side itself, efficiency is going to play an important role. The capex of the electrolyzers and the lifetime of the stacks. So, and a contribution from all these three is going to be crucial. But then the biggest contribution is going to come from the cost of renewable power. But let's say that's outside the scope of this discussion. At least looking at making electrolyzers both cheaper and more efficient and higher lifetime will contribute partially to the reduction. I mean, I'd say at least out of that $4, you're expecting you could kind of get a benefit about $1.5 if there's work done and improvements on some of these parameters which were mentioned. My last slide, of course, I mean, other than let's say electrolyzer itself, I mean, what are some of the other mechanisms? I mean, one of the things which we are seeing in certain designs where dynamic electricity kind of exists, right? Power tariffs, for example, Australia. So where we are looking at over designing the electrolyzers and then using curtailed power to make hydrogen and store it, right? So that is basically making use of the negative pricing mechanisms. So those are some of the other ways in which we can reduce the cost. And again, I mean, lower capex electrolyzer will facilitate that. In over designing, there will not be a lot of let's say pain from that perspective. Again, co-location specifically with respect to SOECs and combining with other kind of hydrogen production would be useful. So that was my last slide. Thank you.
Thank you, Santosh, very much. We haven't had more questions. I'd like to now invite Mr. Arnab Sinha to give our last talk before we move on to panel discussion. We will not have the break as in the current plan because I think that way we'll have enough time, otherwise you're slightly late. But the floor to Mr. Arnab Sinha.
Thank you very much. I hope you can see my screen, and I hope it is the right screen.
If you would put into a full screen mode.
Yeah. Yep. Are you seeing the right screen?
You have to switch it to a full screen by go to display setting in the top bar. And then perfect.
Should be good now, right? Yeah. Okay. Perfect. So thank you.